In this lesson, we're going to be learning about the probabilities of independent events. The essential question is, how can a model help in finding the probability of two independent events? So Talia is playing a game in which she must choose option 1 or option 2, and then spin the game wheel, flip the coin, and roll the number cube labeled 1 through 6. For her to win a prize, all of the conditions listed under the chosen option must occur. Which option should Talia choose and explain? So if we look at this, option 1, we have to have the game wheel landing on an S. So if we look at our wheel here, there are 15 different sections on the wheel. We need to double check because sometimes there's duplicates, but it looks like there's only one S there, so there'd be a 1 out of 15 chance of getting an S. When we flip a coin, it's a 50-50 chance landing heads or tails, so landing tails would be a 1/2. So this would be our probability of getting an S. This would be our probability of getting tails. And then an even number is rolled. So if we have a regular number cube 1 through 6, half of the numbers are even, half of them are odd. So probability of an even number would be 1/2. And what we'll be talking about here is that actually if we multiply these probabilities together, that will give us the chance of this happening. So 15 times 2 is 30, 30 times 2 is 60, so we've got a 1 out of 60 chance. For option 2, we're looking at the game wheel landing on Z. So if we look at our wheel here, there's a Z. And that looks like it. So the chance of us getting a Z would be also 1 out of 15. It says the coin lands on either side. That's not going to lessen our chances at all. You could say it's a 2 out of 2 chance if you wanted to, but it's not really going to change anything. 2/2 is the same as 1. Multiplied by 1 doesn't change anything. And then a number 3 is rolled. So the number 3 on a regular number cube, 1 out of 6 sides have the number 3 on them. So if we multiply these, keeping it as it is, we would get 15 times 2 is 30, 30 times 6 is 180, and that could reduce to 1 out of 90. So option 2, we've got a 1 out of 90 chance. Option 1, we've got a 1 out of 60 chance. So option 1 would give them a better chance of winning. So we look at example 1. Before we get started with that, we can go ahead and look at a definition here talking about independent events. Independent, basically the one doesn't affect the other. So one event doesn't affect the other event. So if we look at this example, Sadie has 1 ticket left at the school fair and she has not yet won a prize. What is the probability of Sadie winning a prize with flip and spin? So flip and spin, it says flip a head and spin a blue to win a prize. So these are independent events because what we flip on the coin doesn't change what we're going to do for spinning. In other words, I flip a coin, I get tails. That doesn't make me more or less likely to get red or blue or green or yellow. So they're independent. So one way we can look at this, they made a table. They listed out all the possible outcomes like we did in the last lesson. And the favorable outcome, which is winning, would be heads in blue. And if we look at this heads in blue, that only happens 1 out of the 8 times. So again, P and then stuff in parentheses, that means in this case probability of heads then blue would be 1/8 or about 12.5%. Another way of doing it, like I mentioned at the beginning of the lesson, is by doing fraction probabilities rather than listing out the options. So flipping a coin, there's 2 possibilities. The favorable outcome, or the probability of heads, is 1/2. When we spin a spinner, on this spinner there's 4 possibilities. 1 of the 4 is blue, so we got a 1/4 chance. So if we take those 2 probabilities, the 1/2 and the 1/4, we multiply those together. That's another way we can show our probability of getting heads and then blue would be 1/8 or 12.5%. We're mainly going to focus just on the fraction answers with these unless they ask us to write a percent. And for finding the percents, what you can do again is just divide the numerator by the denominator, move your decimal 2 places to the right. So for this example, 1 divided by 8, if we divide that out, we would get 125 thousandths. And then just move the decimal 2 places would give us the 12.5%. On the Try It, the designer of Flip and Spin creates a new game using a 5-section spinner. How does the new spinner change the probability of winning a prize? So if we look at this, if we consider the same options for winning a prize, the chance of getting, basically what we're looking at, the book's not really showing this real great, but probability of heads and then blue is what we're looking at again. So probability of getting heads is not affected by that spinner because these are independent events. We've still got a 1/2 or 50% chance of flipping the coin and it being heads. And then for the spinner though, this time we've got 5 sections, so that would be a 1 out of 5 chance. And again, if we multiply those, that would be a 1/10 chance of winning the prize. 1/10, if you divide that out, obviously would be 1/10, and then move your decimal 2 places, that would be the same as 10%. So since it says equals blank or blank, we would want to put both representations there, so the 1/10 or 10%. And then it says it is blank likely that a player will win a prize when using the 5-section spinner than when using the 4-section spinner. So with the 5-section spinner we have a 1 out of 10 chance. With the 4-section spinner we had a 1 out of 8. So 1 out of 10 versus 1 out of 8. With the 5-section spinner, then it is less likely that a player will win a prize. Example 2 talks about we can use a tree diagram. what is the probability a coin flipped 3 times will land up tails all 3 times? And for a problem like this, this is an option for us. Sometimes, depending what we're doing with flipping coins and things, sometimes doing a tree diagram or a table or something is going to be a beneficial way of finding the answer. So you can see they mapped out their different possibilities here. Getting tails all 3 times is just the route way on the right side here, and you can see there are 8 routes altogether, and there's only a 1 out of 8 chance of getting all 3 tails. And again, we can't always do it this way, but for this problem we could actually look at probability of tails and then tails and then tails. Probability of tails is 1/2, probability of tails is 1/2, probability of tails is 1/2, and we multiply and we would get 1/8 that way also. So for this one we could get by, as long as they didn't specify that we have to do a tree diagram or a table, we could actually figure it out that way. Now if we look at the try it, it says, is it more likely a coin flip 3 times will land heads up exactly once or will land heads up exactly twice? For a problem like this, it's probably better to do the tree diagram or somehow do the sample space of what all the different options are. So for this one, we're flipping it 3 times. The question is heads up exactly once or heads up exactly twice. So if we look at our tree diagram here, heads up exactly once, just going through here, there's one that's heads up exactly once, there's another one. So heads up exactly once, oh whoops, missed one. Heads up exactly once, that's a 3 out of 8 chance. Heads up exactly twice, is also 3 out of 8. So for this one, since they were the same, we could just say they are equally likely. And again, this one would be, it wouldn't work out very well to try to do it by multiplying fractions and things like we've talked about on some of the other problems. Kind of the reasoning for that is it's not asking for just one certain case. It's kind of a, in other words, it's not all tails, it's not all heads, it's kind of a combination there. So that makes it a little bit more difficult to figure out that way. Example 3, what is the probability a coin tossed 3 times will not land heads up all 3 times? So this has to do with complementary events. So complements of something is kind of like the opposite of something. And complement, kind of an example, if we talk about the weather, maybe we could talk about rain or no rain. So if they say the chance of rain is 80%, we could say the chance of no rain is 20%. Okay, now obviously there's other stuff we could talk about, just a precipitation chance. There's other variations of precipitation, sleet, snow, different things like that. But just for that example, those would be, that's an example of complements of each other. So that can help us because if you look on this problem, the chance of getting all 3 tails was 1 out of 8. And so it's either going to be all three tails or not all three tails. And those are complementary. They add up to 100% or they add up to 1. In this case, 8/8 we could call it. So they're 1 here if you want to look at it. Think about it this way as like 8/8. So 8/8, take away the 1/8 would leave 7/8 chance that it's not tails up all three times. So if we look at the try it, Casey will toss 2 coins. What is the probability of the 2 coins landing heads up? And then what is the probability of the 2 coins not landing heads up? So probability of them both landing heads up, since those are both doing the same thing, there's nothing else going on here. We can actually do our fractions. So chance of getting heads would be 1/2. Chance of getting heads would be 1/2. Multiply those would be 1/4. And so we know either they're both going to be heads up or not. So if we talk about them not being heads up, we know that's like 1 minus 1/4, or you could think of 4/4 minus 1/4 would leave us with 3/4 chance that they don't both land heads up. Example 4, Shannon will roll 2 number cubes numbered 1 to 6. What is the probability that the sum of the numbers rolled is either either even or equal to 11? So the sum is either even or equal to 11. So we can look at this one again. A table or some kind of sample space is going to be very beneficial here. So this one, they've marked this, they've shaded the even sums as red. So for example, if we got a 1 and a 1, that'd be a sum of 2. If we got a 1 and a 3, that'd be a sum of 4, and so on. So you can see we got kind of a checkerboard here. Beyond that, we have 2 of these highlighted in yellow that are sums that are equal to 11. So if we got a 5 and a 6 or a 6 and a 5, those would equal to 11. So if we look at this, our even sums, there were 18 out of 36 options, which reduces to 9 out of 18. Probability of the sum equaling 11, there are 2 out of 36, which reduces to 1/18. Now if you'll notice, the 9/18 could have been reduced to a half. The deal is, though, if you look at the next part of the problem, we have a fraction with a denominator of 18. So when we're going to be adding these together, because we don't care if it's an even sum or a sum equal to 11, either one of those is fine. We know we're going to be adding them. We want our denominators to be the same, so that'd be a reason to just keep them the same. In fact, we could have just kept them both as 36 and then added them and then thought about reducing after that. Anyway, we add these together. We've got 10/18, and then we can reduce that to 5/9. So there's a 5/9 chance of getting either an even sum or a sum that's equal to 11. Example 5, Quincy will roll 2 number cubes numbered 1 to 6. What is the probability the sum of the numbers rolled is either even or greater than 10? So this is a very similar problem here, even or greater than 10. Or means we don't care, either one is fine with us. So we got our checkerboard here again. We've got 18 out of 36 that are even, and greater than 10 would just be 11 or 12. So you can see 3 out of the 36 that are greater than 10. And so then we would just add those probabilities together. So 18 out of 36 plus 3 out of 36 is 21 out of 36. If you'll notice here, though, they're subtracting 1 out of 36 to get their answer, which should be reduced here, by the way. We can reduce both of those by 4, would be 5/9. The reason they subtracted out that one option is that one of the possibilities is having an even number that is greater than 10. If we get a 12, that would be both even and greater than 10. Another way of doing that, rather than worrying about subtracting that out, is we could just count all of our different possibilities. So, shade or circle all the different ones that would work. So, we've got a 2, 4, 6, 4, 6, 8, and so on. And I know they've got them shaded here for us already, but if we just look at all these different possibilities like that, then we're not going to count that 12 twice by just circling it. So we just count and when you count those up, there's 20 out of 36 there. So that may be a nicer way where we don't have to worry about, what do I need to subtract off, or do I need to subtract something off. We can just count them and say there's 20, and then 20 out of 36, reduce it and get your answer. And what's happening there, what the book's talking about, is that these events are not mutually exclusive. In other words, there's an overlap there. I didn't talk about that earlier. If they're mutually exclusive, that means there's no overlap. But in this case, we do have an overlap because we have a 12 that's both an even number and a number that's a sum greater than 10. So if we look at the try it, Jamie will roll 2 number cubes numbered 1 to 6 and find the sums. Are these events mutually exclusive? So rolling sums of 6 and multiples of 3. So if we think about multiples of 3, we could have 3, 6, 9, 12. If I'm only rolling 2 number cubes numbered 1 to 6, 12 would be the biggest total that we could have. 3, 6, 9, and 12 are the multiples of 3. Otherwise, they're saying sums of 6. Well, 6 is already a multiple of 3, so the question is, are these mutually exclusive? So the answer would be no, because there's an overlap there again. Another example here, rolling odd sums and multiples of 2. Multiples of 2, 2, 4, 6, 8, 10, 12. And odd sums, well, odd sums would be 1, 3, 5, 7, 9, 11. Those, there is not any overlap. So are they mutually exclusive? Yes, they are exclusive. There's no overlap. Okay, again, that's a way to think about it. No overlap if they're mutually exclusive. In this case, there was an overlap, and so they were not mutually exclusive. So if we look at the key concept, 2 events are independent if the outcome of one event does not affect the outcome of the other event, and to determine the probability of 2 independent events, multiply the probabilities of each event. If we look at the do you understand number 2, how can you use the probability of the desired outcome to find the complement of an event? So you can find the complement by subtracting from 1. So if one event, one probability of something is 1/5, if you take 1 minus 1/5, the complement would be 4/5. Look at the do you know how number 4. one of 3 contestants will be randomly selected to win a prize. One of 3 different prizes will be randomly awarded to the contestant whose name is selected to win. The tree diagram shows all possible outcomes of this contest. So the question, what is the probability that Whitney will win prize 2? So first of all, and basically what we're doing here, looking probability of Whitney and prize 2. So first of all, if we look at this, one way of doing this, looking at the fractions in this case, Whitney, there are 3 people, so she's got a 1 out of 3 chance that her name is going to be drawn. And then if she's drawn prize 2, well, there are 3 prize options. So getting prize 2, that would be a 1 out of 3 option. And if you multiply those altogether, that would be a 1/9 chance then of choosing Whitney and prize 2. And again, you could also on this one, since they've got the tree diagram drawn out, we could just look at all the different paths. There are 9 different paths, and only one of those paths, that would be Whitney and prize 2. So that would be another way. Since they already drew the tree diagram, that would be maybe an easier way even to find the probability of that happening. If we look at number 5, the table shows all the possible outcomes for flipping a coin and spinning the pointer of a spinner with 4 equal sized sections labeled 1 through 4. And they made that table there really sums it up nicely for us. What is the probability the pointer will not stop on 3 and the coin will not land on heads? So since we've already got the table here, we're looking, it's not a 3 and it's not heads. So not a 3 and not heads. Well, this one's got heads. This has got heads. We can eliminate all those options. So if it's not landing on heads, it's landing on tails, not stopping on a 3, so we can eliminate the tails 3. And so you can see here we've got a 3 out of 8 chance of that happening. Another way, if we didn't have this table already drawn, we could look at, again, probability of not 3 and not heads. So not 3, it could be 1, 2, or 4. 1, 2, or 4, that's 3 options out of 4 numbers. Not heads would mean tails, and we know the chance of tails is 1/2. And then we could just multiply 3/4 times 1/2 would be 3/8. Part B, what is the probability that either the coin will land on heads or the spinner will land on a 3? So we don't care which one it is here. So if it lands on heads, we're fine with that on this part B, so any of those options would work, or if it lands on a 3. So tails and 3 would work also, and so altogether that's 5 out of 8 options. And again, having that table there is going to make that an easier process for you. Again, we don't have to worry about mutually exclusive and things like that, any overlaps that might be happening there. So I'd like you to do page IN18, numbers 6 through 17. One thing to note, just to make sure everybody's clear, on number 10, on the table there, the first digit is on top. And the second digit is on the side. So for example, we got the at the top of 1, on the side we've got a 5. How they've got it set up, that would be first digit, second digit, that would be 15, for example. Okay, that'd be your top corner there, just to get you started with that. So this gives you an idea how to find probabilities of independent events.